In this lesson, we're going to start talking about the concept of a definite integral. So if you recall, in the last section, we were interested in finding the area under a graph of a function f of x, the area between the graph and the x-axis, and in some intervals from a to b. What we decided to do to approximate this was to break this up into subintervals. Take the interval from a to b, divide it into smaller pieces, and then for each of those pieces create a rectangle that would be approximating the area under that graph. And we did it with rectangles whose left corner was on the graph, ones with the right corner on the graph. Even talked about what happens if the midpoint is on the graph. So what we have here is just basically taking any point in the subinterval, whether it's the left point, right point, midpoint, or doesn't even have to be in the middle. At that point, find what the value of the function is, and then create a rectangle at that height. Right? So in each subinterval, we're picking a point. At that point, find the value of the function, and then create a rectangle with that height. Right? And then to find the area, we are going to multiply the height of each of these rectangles by the width, which we call delta x, and then add them all up. Right? So the delta x is basically the difference from b and between b and a. So b minus a tells me how long this interval is, and then we're going to divide it into n rectangles, and that tells me how wide each rectangle is. Okay. Now we saw that the more rectangles we have, basically the smaller these rectangles are, right? So the more rectangles we have, the smaller delta x gets because the denominator gets larger, and they will fit better around this graph, and they will approximate the area much better. And again, the more they are, the better our approximation. And ideally, if we could somehow get to have an infinite number of rectangles that would be really, 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 really thin, that would be infinitely thin, and they would approximate the area. Well, it won't be an approximation anymore. They would give me this area exactly, right? And that's what we call a definite integral. So as a definite integral, we take the value of the function at each point, multiply by the width, that gives me the area of each of the rectangles, then add them all up. So remember the Greek letter sigma, capital sigma, means add. Add all of these rectangles from the first one all the way to the nth one. So if there's 6, we add all 6 of them. But ideally, what we want to do is let n go to infinity, so have infinite number of these rectangles. Delta x gets very, very small, and that would give me the exact area. And that is what we refer to as a definite integral, right? So we use this elongated s for our integral, and there would be 2 limits on this integral. The bottom number would be the lowest part of that subinterval, and the top number would be the upper end of that subinterval. And we're doing that for the function f of x. That's the function I want to find the area for. And the dx tells me what my independent variable is. Right? So if we had multiple variables, it tells me x is the independent variable. Right? So one thing we will run into is the fact that sometimes our function goes below the x-axis, and if I'm finding the value of the function, the values could be negative, right? So anything that's above the x-axis would have a function value that's positive. The things that are below the x-axis would have a negative value. And basically, these would get subtracted rather than being added. So we're adding a negative number. And that's what we refer to as the net area, right? So anything that's above x-axis would be positive, anything below x-axis is negative, and it could actually be that my entire area ends up being 0 because the negative numbers could cancel the positive numbers, right? So that's again, that the idea of the net area is the fact that when we have something below the x-axis, we look at it as being a negative area. Okay, so can we always do this? Can I always find a function? Well, the integral of a function. Well, the integral function is defined as the limit as n goes to infinity of some sum, so that limit must exist. And as far as the function itself is concerned, as long as f is continuous on that interval, or if it's not continuous, as long as it has only a finite number of jump discontinuities, then it would be integrable. That means I can find its integral. And then the definite integral will exist, and that would give me the area that I was interested in. Okay, so I need to have a continuous function, or if it's not continuous, it can only have a finite number of jump discontinuities to be integral. Okay, so next thing we're going to look at are some properties of integrals. The first property says if f and g are continuous functions, so I have two functions in here. Originally, I'm only looking at one. In the next slide, we'll look at both f and g. As long as they're continuous functions, the following properties will hold. So if I have a function whose integral goes from a to b, and I switch the limits to go from b to a, the integral that I get is going to be negative of the original integral. So if this was 7, this is going to be negative 7. Right? And that hopefully makes sense because if you remember when we were adding those areas to start with, they were all multiplied by delta x, and delta x was calculated by taking b minus a over n. And now if I switch this, I'm going to have a minus b over n. And if I have to go from b minus a to a minus b, that changes the sign. And so I get this extra negative for the width. And since it's multiplied by every rectangle, that means when I add them, there will be an extra negative in front of the whole thing. Right? So the next property says if I have an integral from a to a, that is going to be 0. Right? And hopefully, once again, that makes sense. If I'm going from a to a, I basically don't have any width to my rectangles, and the area that I add up is going to be 0. Next property says if I have a constant as my function, so I don't have f of x, I have just a constant, so f of x is equal to c, then that integral from a to b is equal to c multiplied by the quantity b minus a. And let's see why that should make sense. If I am integrating the function c, that means I have a horizontal line, right? So if my function's constant, it's a horizontal line. So what I'm integrating is really the area on the horizontal line, which is just a plain rectangle. And area of a rectangle could be found by taking the width of the rectangle, which would be b minus a, multiplied by the height of the rectangle, which is the value of the function c. So there's really no need to break this up into smaller pieces. It's just one flat rectangle, so I can just multiply c times b minus a. Next property says that if I'm multiplying a function by a constant and I'm integrating it, that would be the same as integrating the function first and then multiplying it by a constant later. And again, this should also make sense if you think about it. If I, let's say, double a function, so if I have 2 times f of x and my function's twice as high or tall as it used to be. Therefore, the area under it is going to be twice as much as the area I used to have. So if I multiply the function by 2, that's the same as multiplying the area by 2. Okay, so those are some of the properties. We're going to look at a few more in the next slide. So the next property that we have says if I am adding two functions and I integrate, that's the same as integrating the functions first and then adding the results, right? So again, as long as f and g are continuous, remember that condition applies to these also. And if I'm subtracting the functions and I'm integrating, that would be the same as integrating first and then subtracting. And again, as if you think about this as areas, it should make sense. If I add two functions together, it gets taller as long as these are positive values, and I would get the bigger area, and it would be the area of the two combined. Okay, and same logic for subtraction, right? So the next property says if I am integrating a function from a to b, I can pick any value c that I want and integrate the function from a to c first, and then go from c to b separately, and then add the results. Okay, and c could be any number. Now, if you think about it, and that value is between a and b, it should be obvious. If it's outside the interval a and b, it still works because of the property with the negative sign that we had seen earlier. But basically, it says if I have some area going all the way from a to b, I can break it up in the middle, find the first area first, find the second area, and then add the two areas together. And that would give me the same answer as if I had taken the whole thing at once. And then we have three properties that we refer to as comparison properties. It lets me compare my function to some other value or a function to another function. So assuming in my interval I always have a smaller than b, and my function is always positive when I'm inside of that interval. So if x, whenever I have x that's between a and b, the function is positive, then when I integrate it, it's going to give me a positive answer, going to give me an answer that's bigger than 0, right? So again, if you think about it, if my function's always positive in my interval, it means it's above the x-axis, and when we're talking about the net area, we agreed that anything that's above the x-axis, the integral should be a positive value. If I have a function that's bigger than another function in my interval, and for any value inside of my interval, f of x is bigger than g of x, that means it's higher than g of x. If I look at its graph, its integral is going to be bigger. Again, the area is going to be bigger because it's higher than the other one. And the last property we're going to look at says if I have a function that's sandwiched between two values, lowercase m and uppercase m. So it's bigger than some minimum, smaller than some maximum. So it has a minimum in an interval and a maximum in an interval, somewhere between two fixed numbers. Then its area is going to be between the area of the two rectangles that would be formed, right? So m times b minus a would give me the area of a rectangle that's created at the value m, and capital M times b minus a would be the area of the rectangle created at the capital M. So my function as area would be between the area of those rectangles.